Okay, I'm back, and now we want to start our tour of the different kinds of simple machines by explaining how a lever works. And so a teeter-totter is an example of a lever. Now, do you notice anything unusual about this picture? So this lever is in balance. We've got a heavy person on this side over here. We've got a light person on this side over here. But what do you notice about the picture? That the light person is located a further distance from the pivot point than what the heavy person is. And so this is the principle of how a lever is going to work. Now the pivot point, we're going to call that the fulcrum. So the fulcrum of a lever is going to be where it's going to be pivoting. There are going to be three different kinds of levers. The teeter-totter is an example of a first-class lever. So take a look at your first-class levers, and you'll notice that you're going to put in a certain amount of force on one side over here. So we'll say F and then in. So you put in a certain amount of force into the lever, and then what it's going to do is it's going to produce a force on the other side. So this is going to be force out. And then you're also going to have a distance, so that we use the letter R for distance. So this is going to be the distance that goes into the lever. And then this distance over here on this side, so that's going to be R out. And all that we have to do is we're going to say that the work W that goes in has to equal, so think about the fulcrum as being the equal sign, has to equal the amount of work that comes out of the lever. Now again, this is a perfect machine. We're assuming that this is a perfect machine and all of the work that you put in is going to come out. So that's just going to make it easier to do our calculations. So what's the definition of work? Well, it's going to be force multiplied by distance. So we're going to multiply the force that we put in times the distance we put in, and then it has to equal the force out multiplied by the distance out. So that all three of these, the first class, the second class, and the third class levers, work the same way. So here we got the teeter-totter. Another example of a first class lever is going to be scissors. So think about when you have a pair of scissors like this. Okay, so here's the handles over here. Where do you put the paper? Have you ever tried to, let's say you put the paper right there and then you squeeze the handles, how effective is it in cutting the paper? Not as effective as when you take the piece of paper and you put it closer to the fulcrum. So out here, that's where you're going to apply your force. This is going to be the distance to the fulcrum, so that's going to be R in, and then it's going to apply a force on the paper, and then the paper is going to be located a certain distance from the fulcrum. So the closer you get it to the fulcrum, the more leverage you're going to have when you're trying to cut something. Okay, let's look at a second class lever. So what do you notice about the diagram for the in and the out and the fulcrum? Do you notice it's been reshuffled so that the in is still on this side over here, but they put the out in the middle, and then the fulcrum is on the outside. So that's going to be called a second class lever. So a couple examples of this would be a nut cracker. So in the case of a nut cracker, you've got, here's the fulcrum, right? It's on the outside, and then you're going to put the nut right here, and then you're going to apply the force out here. So this is going to be the force that goes into the machine. Then this is going to be the force that's being applied to the nut. So that's the force out. And then here's where the fulcrum is located. So notice how you measure the distance. So you would measure the distance to this force is going to be this whole distance. And then the other distance is going to be this distance right here. And another example of this is a wheelbarrow. So when you are using a wheelbarrow, where do you put your hands? So you put your hands at the end of the wheelbarrow, and then where is the load? So the sand or the bricks or whatever you're trying to carry, they are located here. And then where's the wheel on the wheelbarrow? It's over here. So it's another example of a second class lever. So notice that both the first class lever and the second class lever are going to increase your force. You put in a certain amount of force, and then you get out a bigger amount of force. Now the third class lever is different. So in the third class lever, you put in a large amount of force, and you get out a small amount of force. And so you're saying to yourself, well, that doesn't make sense. Why would I want to do that? Well, in this case, the third class lever is going to multiply distance. So let's say that you're at a restaurant, and you know that they got these sneeze guards. Okay, so the idea of a sneeze guard is if you sneeze, it's not going to get on the food. So let's say that you want a baked potato, and there's the baked potatoes under the sneeze guard, but how do you get them? Well, they give you a pair of tongs, and you're supposed to take the tongs, put them under the sneeze guard, grab that potato, and then pull it back out. What do you notice? It takes a lot of strength to squeeze those tongs and grab that potato. But what's the advantage? It increased the length. So the length of the tongs allows you to reach underneath the sneeze guard and grab the potato. So if you look at the chopsticks, it's the same thing. The thing that you're trying to grab is located far away from your hand. So it increased your distance, but the problem is you have to apply more force in order to do it. The other example of this is your muscle. Okay, so your arm here is an example of a third class lever. So let's say that you're trying to lift something out here. So do you see what a large distance that is? And your muscle, this muscle here, is attached to your arm right about there. And so you got this small distance and you got the big distance. And this would be a certain amount of force here, but your arm here has to exert a larger force than what you're trying to actually lift, because it's got the larger distance. So the third class lever increases your distance at the expense of force. The first and the second class levers will increase your force at the expense of distance. Now, of these three, the only one that I want you to know, if you're one of my students, is the first class lever. And so let's take a look here. How much force would it take to lift the 100 Newton box shown below? Okay, so it's a teeter-totter. You have a 100 Newton box. You can see that it's 2 meters from the pivot point, the fulcrum. And then you're going to push down on one side of the teeter-totter with a certain amount of force, and you can see it's 3 meters from the pivot point, and you need to know how much force do you need to push with in order to lift that 100 newtons on the other side. So we're going to say work in equals work out. Work in is going to be force in, distance in, and that's got to equal the force out and the distance out. Now the force out is the 100. So that's the force that's coming out of the teeter-totter. And the distance out is 2. And so we're going to take the force in, which we don't know, times 3, and it's going to equal 100 times 2, and solve that, and it turns out to be 67. Okay, and then what's the official metric unit for force? It's going to be the Newton. So 67 newtons is the force that you're going to have to apply. Now, in actuality, you're probably going to have to put in more force in order to do it, because some of that energy from that force is going to be turned into heat at the pivot point. All right, let's take a break. When we come back, we're going to talk about the pulley.